and welcome back, everyone. So today we're going to start on the topic of mathematical proofs. So this is the topic that we've sort of been gearing up for. This is what the class is all about, and this is where the good stuff really starts. So let's jump right in and start talking about direct proofs, because this is sort of the simplest and most intuitive kind of proof, and probably, it just follows sort of a natural line of reasoning, so it'll feel more natural to you. So most of the time when we're proving mathematical statements, we're proving statements of the form A implies B. Even when a statement's not expressed explicitly in the form A implies B, we can almost always rephrase it in that form, A implies B. So this method of direct proof for statements of the form A implies B applies to really practically everything that you'll ever do. So how does this work? Well, really, it's a pretty straightforward process. If you want to prove A implies B, you start by assuming A is true. So A is the hypothesis here, and you start by assuming that that hypothesis is true. And then, through a sequence of logical implications, you arrive at B is true, the conclusion. So, it looks something like this. Suppose A is true. Show A implies some intermediate fact, let's say Q0. Now remember, when we use that double barred arrow, that's logical implication. So what you're showing is that A implies Q0 is true. And then show Q0 in turn implies some intermediate fact, say Q1. And so on and so forth, until you finally arrive at some final intermediate fact, let's say Qn implies B. And the logical basis for direct proof comes from a tautology called Modus Ponens. So Modus Ponens is this logical structure here. P and P implies Q is a tautology. So because that is a tautology, it follows from that if you can show if P is true, and so that's your starting point. P is your hypothesis. So you got to have some sort of true hypothesis, and P implies Q is true. Remember, that's the same thing as this. Then Q is true is what this tautology is telling us. So if you know P is true and you can argue P implies Q is true, then it must be the case that Q is true. So that's the logical basis for it. But like I said, this is the most natural way of doing proofs, and it basically amounts to start with whatever the hypothesis of the statement is, suppose that's true, and then just string together a sequence of implications that arrives at the conclusion that you're trying to argue is true. So let's do an example of that here at the bottom. We're going to prove that if n is an even integer and m is an odd integer, then m plus n is odd. Now when you're doing a proof, you always want to identify what is the hypothesis that you're going to assume is true and what is the conclusion that you're going to try to argue is true. Well, in this case, n is an integer and n is an even integer and m is an odd integer is your hypothesis. And then the conclusion that you want to argue is true is that m plus n is odd. So let's start by supposing that that hypothesis is true. So we'll start off by supposing that n is an even integer and m is an odd integer. Okay. Now we know eventually, I'm just going to put it at the bottom here somewhere, but eventually we want to conclude that m plus n is odd. That's our target. Okay. So we want to get from what we started with to m plus n is odd by stitching together some observations. At this point, all we know is n is even and m is odd. Well, we have definitions for those words, even and odd. And so that gives us one step of an implication. So maybe we could say something like this next. Well, because n is even, I'll use a little shorthand here. There exists some k in the integers such that n is equal to 2 times k. Also, because m is odd, well, we know the definition of odd says that m would have to equal 2 times an integer plus 1. So we'll say there exists some integer. Now I don't want to use k again. I've already used k, so I need to use a different variable here. So let's say there exists an L in the integers such that m is equal to 2 times L plus 1. Okay, so this is sort of an intermediate implication or two that we can use. So at this point we know n is 2k and we know m is 2L plus 1, and we want to make some conclusion about m plus n. So it sort of jumps out at me that I should take those two ways to express m and n and add them together. So let's do that. So now m plus n, we have an expression for m, that was 2L plus 1, and we have an expression for n, which was 2 times k. And I'm wanting to say that this thing that I have here is odd. And so if I want to say that it's odd, I need to express it as 2 times an integer plus 1. Well, to do that, I'll just gather the terms that have a 2 on them together. So like this, 2L plus 2k plus 1, which is in turn equal to 2 times L plus k plus 1. And observe that L plus k is an integer. We know this from the axioms of integers. Any two integers added together is an integer. So look at what we have. We have m plus n is equal to 2 times an integer, here this L plus k, 2 times an integer plus 1. Well, that's the very definition of what it means to be odd. So we can conclude now that m plus n is odd. And once we have arrived at the conclusion, the proof is done. Put our little square. All right. So the big strokes of this are, we started with the hypothesis that m is even and m is odd. That was our hypothesis. We supposed it was true. And then, through a sequence of implications that can come from definitions or other kinds of arguments, we arrived at the conclusion that we wanted, which was that m plus n is odd. All right. So this will be our go-to method for proving things, and we're going to end up practicing direct proof a lot more. But I want to go ahead and move on to a few other methods, and we'll be using direct methods as we go too. But let's go on to some other methods so that we get a wider variety of tools in our tool chest for proving things. So our next method is called the method of contraposition. And we use it to prove statements of the form A implies B, just like the direct method. But in this case, we're going to take advantage of a certain tautology, and you've probably guessed what tautology we're going to use. It's the one that tells us that the contraposition of A implies B is equivalent to A implies B. So that tautology is P implies Q is logically equivalent, so that's the double barred arrow, to not Q implies not P. So if I want to prove P implies Q, I can prove not Q implies not P instead. So when I apply that to A implies B, that'll be not B implies not A instead. So to prove A implies B, we're going to prove not B implies not A instead, because those two expressions are logically equivalent. So if this is true, if I can argue that that's true, then that means that the original statement must be true also. All right, so let's try that with this example. We'll discuss in a minute why this example is a good one to do with the method of contraposition, but for now let's just go with it and try the method. In this statement, we need to identify what's the original hypothesis, A. Well, this is the original hypothesis A, that 5n minus 7 is even, and we want to argue that this conclusion is true, that n is odd. So what we need to do is look at the contraposition, and we want to prove not B implies not A instead. So we're going to prove this directly using the direct. We're going to use the direct method to prove that the contraposition is true. So to do that, we'll start off by supposing that not B is true. Proof. Let's suppose n is not odd. That is, suppose n is even. So what we've supposed here that n is even, that's our not B. And then we're going to eventually want to prove that not A is true. So not A would be the statement that 5n minus 7 is not even. And of course, not even is just the same thing as odd. So our target is to prove that all this, that our original hypothesis, n is even, implies that 5n minus 7 is odd. So this is our target statement to prove. All right, so let's see if we can make some headway with that. I think it's a good idea to keep an eye on what your target is. Okay, so if I want to prove 5n minus 7 is odd, I need to get my hands on that expression. I need to show that it's 2 times an integer plus 1. But first, let's take advantage of our hypothesis that n is even. So since n is even, we know that there exists some k in the integers such that n is equal to 2 times k. So now I've got this to work with, that n is equal to 2 times k. So it kind of makes sense to, at this point, let's take that expression for 2k and substitute it into the expression 5n minus 7 and see if we can make some progress with it. So now I can say, well, 5n minus 7 is the same as 5 times 2k minus 7. So that's the same as 10k minus 7. And I want to see if I can write that as 2 times an integer plus 1. Well, this is a little bit of a tricky one, but here's what we can do. I need a plus 1. So what I'm going to do is take that minus 7 and write it as minus 8 plus 1. I'm going to go ahead and erase our target here, so just to make a little room. And now I can take that and take the first 2 terms of it and factor a 2 out. So I'd get 2 times 5k minus 4 plus 1. And I want to point out that this expression 5 times k minus 4 is an integer on account of k being an integer. So if you take an integer and you multiply it times 5, you still have an integer, and subtract 4 from that and you still have an integer. So now look, our 5n minus 7 is 2 times an integer plus 1. Well, that's the very definition of what it means to be odd. Thus, we can say 5n minus 7 is odd. And now we've proven by contraposition that if 5n minus 7 is even, then n is odd. One thing almost always I will do, I didn't do it this time, but what I usually do as a matter of formatting and to let the reader of the proof know that I'm going to do a proof by contraposition at the very beginning. So here I just kind of said in my proof, if you were reading this proof, you might not know what I was doing until you got to the very end and you went, oh, he was doing contraposition. Now I see why he said n is not odd at the beginning. So what I usually do is up front, in full transparency, go ahead and tell the reader that I'm getting ready to do a proof by contraposition by doing something like this. I'll say parenthetically here, by contraposition, right at the very beginning of the proof. That lets the reader know, oh, if they're going to do contraposition, they're going to suppose the negation of the conclusion, the not B, and then they're going to try to argue the negation of the original hypothesis, not A. And that's exactly what we did, right? N is not odd, that's our not B. And then at the very end here, we figured out that 5n minus 7 is odd, that was not A. So we proved A implies B. So there is a proof by contraposition. It may seem a little weird at first, but after you've done a few of them, it's a pretty natural thing to try. Now, how did I know to do a proof by contraposition? Well, let me show you what would have happened if you would have tried to do a proof by a direct method. Well, if you tried to do this proof directly, you'd say, well, suppose 5n minus 7 is even. That's the hypothesis of the statement we're trying to prove. Then, you'd use the definition of even and say, well, then there exists some k in the integers such that 5n minus 7 equals 2 times k. And now you would have to take this equation that involves n and k, and you want to deduce something about n. In particular, you want to try to deduce that n is odd. But the only thing I can really tell to do with that equation would be to maybe try to solve for n. So I'd have like 5n equals 2k plus 7. And then I would have, by dividing both sides by 5, I could get n is equal to 2/5 k plus 7/5. And at this point, I've got some weird fractions involved, and I don't see any way to, looking at the right-hand side of that expression here, I don't see why that would tell me that n is odd. I mean, in the definition of odd, it doesn't have anything to do with fractions 2/5 and 7/5, and yeah. So you get kind of stuck right here. It's just like, what do you do? So sometimes that happens, and whenever I see that the hypothesis is sort of a complicated expression and the conclusion is sort of a simpler statement, sometimes if you do the contraposition, it makes your hypothesis the simpler statement, and then you can try to prove a more complicated thing based on that simpler hypothesis. So anyway, that's an idea for how to get started on those. Generally speaking, I usually start by trying to do a direct proof. And if the direct proof gets stuck like this one did, then I may go, what happened if I tried to do the contraposition? Would that simplify matters a little bit? And as you start to develop some experience and intuition, you may not actually have to go through the whole process of trying to do the direct proof. You'll just know from the beginning that, like, I can tell this one's probably going to be easier to do by contraposition because, when I switch the hypothesis and conclusion and I negate them, it just forms a simpler statement. So anyway, this one you just get stuck and really can't go anywhere with it when you try to do it directly. So yeah, that's how I knew this wasn't going to work. All right, so now let's try another method of proof called proof by contradiction. So proof by contradiction is a method that's based on a little bit of fancy logic. And let me try to explain the logic to you before I show you how the method works. What we're going to do, suppose you just have some statement A. I'm going to give that general statement a name of A, and I want to prove that statement A is true. And C is going to be just any old contradiction. So C is just a statement that is false. That could be anything in the world that's false. It could be 2 plus 1 equals 5. It could be that 3 is even, etc. It doesn't matter. Just something that is verifiably false, okay? But just think of it in general terms, right? C is just some arbitrary contradiction, some false statement. Now, let's suppose that you can argue that the negation of A implies C is true. So I'm not saying that not A or C, I'm not saying anything individually about their truth values. I'm talking about the whole implication, not A implies C is true. In other words, you can argue that this statement here is true. You can make a proof of it. So suppose you can prove that not A implies C is true. Well, let's think about the logic of that a little bit. Not A implies C is true. This statement that not A implies C is true is logically equivalent to saying that A or C is true. Now that may be difficult to see. Let me give you a hint as to why it's true. So to understand this implication right here, it kind of comes down to, we had a tautology that said not P implies Q is logically equivalent to P and not Q. So from there, you can get this tautology. If you negate both sides of this, so negate here and negate here like this, then you end up with, on the left-hand side, P implies Q because you got 2 nots is logically equivalent to, then the negation of an and statement is an or statement using De Morgan's law. So this would be not P or not Q, which is just Q. So we're applying this equivalence here to this implication. And so you end up with two knots on the A, so it just becomes A, and then or Q, which is C. So anyway, that's the justification for that. I'll leave that there for a second, but I'm going to delete it here when I clean up the notes here in a little bit. But anyway, remember here that C, the statement C, is false. Now the only way that an or statement can be true is if one of the two statements in the total or statement is true. But since I know C is a contradiction, it's always false. The only way that this or statement can be true is if A is true. So we got to have A is true here. So summarizing here, if you argue that not A implies C is true for some contradiction C, then A is true. So this is it. Just you have to argue that not A implies C is true. So in other words, if denying A implies a contradiction, then A must be true. Now, typically, when we're trying to prove statements, we're trying to prove statements of the form P implies Q. So think of P implies Q as your statement A, and let's apply the previous logic to P implies Q, where P implies Q is our A from this previous thing up here. So if I want to prove that P implies Q is true, we could deny it. Say, let's deny that that's true, and then argue that a contradiction results. That's what I've got expressed here on the left-hand side. Not P implies Q implies C, where C is a contradiction again. Well, that's the same thing as if you apply the tautology that tells you how to negate an implication, like you have here, then you end up with P and not Q implies C. So if you can prove that P and not Q implies a contradiction, that tells you that P implies Q is true, and that's typically what we call the method of contradiction. So method of contradiction for proving P implies Q goes like this. 1, suppose P is true and not Q is true. Argue a contradiction results, so that's your C, and then you would conclude P implies Q is true. So let's see how that works in practice. Maybe I'll scoot this up here. But yeah, this is the method that I want you to use here. That's the method of contradiction. So let's try it out on an example. In this example, we're going to prove that if 5n minus 7 is even, then n is odd. Notice that that's the same problem that we proved a minute ago using the method of contraposition. We can also prove it using contradiction. So let's see how the proof of that would go if we did it by contradiction. Okay, so on the basis of what we were talking about a little bit earlier, this is P, the hypothesis, that 5n minus 7 is even, n is odd is our Q, and we're trying to prove that P implies Q. So the method of contradiction would have us assume P is true and Q is false. So in other words, and by the way, I'm going to let the reader know at the beginning that I'm doing a proof by contradiction so they'll understand the logic of my hypotheses. So we'll suppose, usually I indicate that I'm doing a proof by contradiction also by saying suppose to the contrary of the statement that's to be proven, that 5n minus 7, the hypothesis, is even, but the conclusion is false. N is not odd. In other words, n is even. Here is P, but here is an and n minus 7 is, n is even is our not Q. So we're supposing P and not Q, okay? Well, let's see what we can get going with this. Well, since 5n minus 7 is even, there would have to exist some k in the integers such that 5n minus 7 is equal to 2 times k. That's the definition of what it means to be even. And since n is even, there would have to exist some L in the integers such that n is equal to, let's say, 2 times L. Again, we don't want to reuse that arbitrary variable k that we used to say that 5n minus 7 was even. It just causes issues because we don't know it's the same integer for both. All right, so now we got it. So our goal here is to come up with some kind of contradiction. What could that contradiction be? Well, conveniently bundled right here, circled in red, are the two things that we know at this point. 5n minus 7 is 2k, and n is 2 times L. So one thing that jumps out at me to do is to maybe try to do a little algebra with those two equations and see if I can get something that's nonsense. So one thing you might try to do is just add both sides of the equation together. So if I took 5n minus 7 and added to that n, so that's the left-hand sides of these equations over here, then I can replace those two expressions with the right-hand sides of those equations. So I could say, well, this is equal to 2 times k plus 2 times L, which in turn implies, on the left-hand side there, I could write that as 4n minus 7. And on the other side, I could write that as 4k. Sorry. I can just write that as 2k plus 2L still. I guess I could write that as 2 times k plus L if I like. And now I think I know what's the contradiction that I want to argue. I think I'm going to try to argue that a number is even and odd at the same time, but we know that that can't be. An integer has to either be even or odd, can't be both. So check this out. On the right-hand side, I can write that as 4n. I'm going to do the trick we did a minute ago and write that as minus 8 plus 1. And I still have 2 times k plus L on the right-hand side. Now on the left-hand side, I'm going to write that as 2 times 2n minus 4 plus 1. And on the right-hand side, I still have 2 times k plus L. So the idea of my contradiction here is to notice that the right-hand side of this equation is even, but the left-hand side is odd because the left-hand side is of the form 2 times an integer plus 1. Notice that 2 times 2n minus 4 plus 1 is odd, but 2 times k plus L is even, but an odd integer cannot equal an even integer. So we have a contradiction. And as soon as you hit a contradiction, that tells you that your original hypothesis was false. In particular, our hypothesis that P and not Q is false. But that's the same as not. So our original hypothesis of P and not Q is really the same logically as not P implies Q. So we know that not P implies Q is false at this point. So in other words, P implies Q must be true. So as soon as you hit the contradiction, though, you know you're done. So you can just go ahead and say the proof is done at that point, because the negation of the original statement that we wanted to prove yielded a contradiction, which tells you that the negation of the original thing was false, which means the original thing is true. Now, the tricky part about doing a proof by contradiction is that you don't know up front what the contradiction is going to be. You just have to take, assuming that the original statement is false, and you have to come up with your own contradiction. Somehow you have to take that information and put it together to get some form of contradiction. And in my case, I came up with an even integer equals an odd integer. But like I said, the contradiction could take any form. It could be that 2 equals 1. I guess that's kind of the same thing as odd equals even. It could be that your contradiction could be that there are a finite number of prime numbers. And we know, in fact, there are actually infinitely many prime numbers. The world is your oyster when it comes to what your possible contradictions are. But that at the same time makes it difficult because you don't know what your target is necessarily. So usually when you're doing a proof by contradiction, you need to do a little scratch work and kind of figure out what your contradiction is going to be before you start really trying to write the proof. Let's try another example of a proof by contradiction. Before we do the proof, I want to remind you of a property of real numbers that you've used many times in the past, and I'm going to give it to you just without proof. It's called the zero product property of real numbers. It just says that for any two real numbers, x and y, if you happen to know that x times y is equal to 0, then it must be the case that one of those two numbers, x or y, has to be 0. It could be that both of them are 0, but at a minimum, one of them has to be 0. So I'm going to use that fact along with the method of contradiction to prove this example, that for positive real numbers, now notice the hypothesis here is positive real numbers, x and y, we want to prove that if x does not equal y, then x squared does not equal y squared. And we're going to do this proof by contradiction. Okay, now let's take a moment and identify what is the p and the q of the original statement. In the original statement, x does not equal y is your p, and x squared does not equal y squared is your q. So we're trying to prove p implies q, and the method of contradiction would have us assume p and not q. I'm going to assume, in doing my proof by contradiction, that p is true, x is not equal to y, and not q is true. Now the negation of q would be x squared equals y squared. Okay? So let's try that. So suppose x does not equal y and x squared does equal y squared. And let's be sure to say what x and y are here for positive real numbers, x and y. All right. Now remember, when we say positive, that means x and y are both not greater than or equal to 0, but strictly bigger than 0. So x and y are greater than 0 is what this means. In particular, x and y are not equal to 0. Okay, so let's see if we can make some headway with this. Now it's usually easier to work with something that you know positively is true. And we know the positive thing that we can say here is that x squared does equal, in the positive sense, y squared. Let's try to work with that. X squared equals y squared implies, just by doing a little algebra, x squared minus y squared equals 0. So that's a standard move. So I added y squared to both sides of the equation. And then I noticed, I remember from algebra class that I could factor x squared minus y squared as x minus y times x plus y. And now I know that I've got the product of two numbers is equal to 0. So now, by the property at the top in the box there, the zero product property, I'm just going to abbreviate that ZPP. By the zero product property, we know x minus y is equal to 0 or x plus y is equal to 0. But we know that x and y are both positive, but since x and y are positive, we know x plus y is positive. So in particular, x plus y does not equal 0. And the only way that an or statement, this or statement, can be true is if one or the other of the two properties is true. But we know that x plus y here is false. So it must be the case that x minus y is equal to 0. Thus, we must have x minus y equals 0. But this implies that x equals y just by adding y to both sides of that equation. And check it out. We know simultaneously at this point, our hypothesis says that x does not equal y, but now we've derived that x does equal y. Well, that's a contradiction if I've ever seen one. X can't be not equal to y and equal to y at the same time. But this stands in contradiction to the hypothesis that x does not equal y. And so I've reached a contradiction and know I'm done. And that's the proof. Anyway, that's pretty cool. Contradiction it's this sort of twisted logic when you first see it, but it's a really useful method. And whenever you do a proof by either contradiction or by contraposition, we call these indirect proofs to, just indicate that it's not just a straight direct proof. And actually, some people don't really like indirect proofs. There are some mathematicians who only as a last resort will use an indirect proof. And would rather have a direct proof, which is considered more constructive. But the logic of it is perfectly fine. But it feels a little bit like a trick. And it kind of is. It's a trick of logic. But it's a handy one, and it allows you to prove a lot of things. So what I would like you to do at this point is to pause your video and try your hand at proving this statement. If m plus n is even and m is odd, then n is odd, using the three methods that we just discussed. First, the direct method, then by contraposition, and then by contradiction. You can do the proof all three ways, and it would be really good exercise for you to sort of cement those ideas in your brain to right now stop and try those three methods. So that's what I want you to do. This may take you a little while, may take you like, I don't know, 15 to 30 minutes to do these proofs. But do it, write them down, and then when you come back from the pause, I will go through all three methods with you. All right, welcome back. Let's see if what you did kind of matches up with what I'm going to suggest. Now, one thing that I didn't talk about earlier, but I feel like I should maybe talk about it now, is that I think it's a good idea before you jump in and you start trying to write your proof, like sort of what you feel like is the answer that you're going to turn into the teacher. You ought to just have a piece of scratch paper where you just sort of work out the ideas sort of loosely and without being worried about the language of how you're writing it. So, or you don't have to be so picky about what you're doing, or you have the freedom to just be messy and try ideas and not worry about erasing it or whatever. So let me start with the direct method and let me do a little scratch work. Maybe I'll do scratch work for all three methods, and then I'll write down the three proofs based on our scratch work separately. So let's do a little scratch work here. Before I do any of these methods, I should identify sort of the logical structure of the statement that I'm going to prove. I'm going to take that m plus n is even and label that as p, and m is odd, I'm going to label that as q. N is odd, let me call that r. So that the statement that we're trying to prove is of the form p and q implies r. So if you're doing the direct method to prove an implication, you just start by supposing that the hypothesis is true. So in the direct method, I would suppose m plus n is even and n is odd. Now, if I'm doing contraposition, what I'm trying to prove is not r implies not p and q. So that's the same as not r implies not p or not q. So then I'm going to suppose not r, which is n is even, and show that either p is false, so p being false would be m plus n is odd, or I want to show q is false. In other words, I want to show m is even. And if I do contradiction, the idea is we suppose that the whole implication, we suppose that the whole thing is false. So negating that whole thing is p and q and not r. So the way it works is we suppose p and q, that's the hypothesis of that implication, and the negation of the conclusion, and then we try to find a contradiction. Well, maybe we should write down what this means. So i.e. we're going to suppose p and q, so that's m plus n is even, m is odd, and not r would be n is even. And then our job is to find a contradiction. So now let's play around with this a little bit more. Let's go to the direct method. Okay, m plus n being even, we know m plus n is going to be like 2 times k, and n is going to be odd, so that's like 2l plus 1. And we're trying to argue that n is odd. So somehow, this should be m is 2l plus 1. Right. Okay, so our hypothesis is m plus n is 2 times k, and m is odd, so 2l plus 1, and I want to try to say something about n being odd. So what jumps out to me is to work with those two equations and solve for n. Well, I could take that first equation and solve for n there and get 2 times k minus m. But then I could substitute what m is from the second equation in here, and that's 2 times k minus 2l plus 1. And now I want to see if I can express n as 2 times an integer plus 1. Well, yeah, I can see it right away. If I take those first two terms and factor the 2 off of them, I'd get 2 times k minus l, and then I'd have a minus 1. That minus 1 is a little bit of a mess for us because our definition of odd, we have to write n as 2 times an integer plus 1. But what I can do is the following. I could say this is 2 times k minus l, and I could write minus 1 as plus 1. Let me do it this way. Minus 2 plus 1. Because then I could take that negative 2 and combine it with the first two terms. So I can factor a 2 out of all that, and I'd get 2 times k minus l minus 1 plus 1. So now check it out. N is 2 times an integer plus 1. So that's what it means to be odd, right? Here, this isn't a proof, right? This is just me doing a little scratch work and kind of getting at it. But I've got the essence of the proof there. I've got the algebra of it. And so I just need to go and write up, a more formal proof in a paragraph form using words and stitching together the ideas and justifying things. But that's the crux of it right there. Taking m plus n, writing that as 2 times k, writing m as 2l plus 1 like we did at the beginning here, and just doing some substitutions and solving for n to express n as an odd integer, 2 times an integer plus 1. Okay, let's go to the contraposition method here real quick, and let's see if we can make some headway with that. So if we've got n as even, right here, right? We've got n is even, so we're going to say n is equal to 2 times k. Now, how do we show m plus n is odd or m is even? Well, I'm going to teach you a little trick right now that's pretty handy. I may have to go off to the side up here somewhere. But we're trying to prove an or statement here, right? Now, it turns out, and you can find this in the list of tautologies, but P or Q is logically equivalent to not P implies Q. Or the other way around too, not Q implies P. So all of these things here, here, and here are all logically equivalent. So anytime I want to prove an or statement, it suffices to prove that negating one of the statements in the or statement implies the other one. Which kind of makes sense, right? In order for an or statement to be true, at least one of them has to be true. So if you say, well, suppose one of them is false, then it must be the case that the other one is true if the or statement's going to be true. So I'm going to take advantage of that down here because I've got to prove an or statement. So what I'm going to prove is if I hold, say, that m is even, I'm going to have that be my, yeah, okay. So like if, let's say that that's your P, and m plus n is your Q, and so then I could do not P implies Q. So I'm going to prove not P implies Q to prove that or statement. So not P is m is odd, so I'm going to suppose that m is odd. So taking advantage of this logic here, we're going to suppose m is not even, so in other words, m is odd. And then that means m is equal to, say, 2l plus 1. And then we can do m plus n and get our hands on that. So m plus n is going to be 2k plus 2l plus 1, which is 2 times k plus l plus 1, which we can see is odd. And that's what we wanted to argue, right? If we held that that was our Q, so we're proving not P implies Q, so that does it. That one's a little bit tricky. You had to know that little trick. So I wouldn't be surprised if you had a little bit of trouble doing the contraposition on this one. I think contradiction is a little easier to deal with. So on the contradiction side of things, we've got m plus n is even, so m plus n is, say, 2k. And we've got m is odd, so m is equal to, say, 2l plus 1. And we've got n is even, so we could say n is equal to, I don't know, 2 times j. And we want to get some kind of contradiction out of that. And I think I'll proceed in the way that I got a contradiction in the previous proof that I did, where I want to argue that an even number equals an odd number, just by doing some substitutions. If I take what I know m and n are individually here and substitute into the first equation, then I would get something like 2l plus 1 plus 2j equals 2k. And what I think you can probably convince yourself of pretty quickly is that this over here is odd, because you can take that and rewrite it as 2 times an integer plus 1, and this side over here is even. And we have that same contradiction as before, that even and odd can't be equal to one another. So those are the 3 sort of bits of scratch work. But notice here, these are not proofs. Even if it contains the idea of the proofs, it's really rough, and no one would be able to really read this and follow the logic of it so well. So we want to write this up into a form that's readable. And so let's do that on the next page. So let me give the 3 proofs sort of written more nicely. All right, so when doing our direct proof, we were starting off with the hypothesis that m plus n is even and m is odd. So suppose m plus n is even and m is odd. And then we can say there exist integers, let's just do them both at once here, k and l, such that m plus n is equal to 2 times k and m is equal to 2l plus 1. M plus n being equal to 2k, we could solve for n to get n is equal to 2 times k minus m, and substituting m equals 2l plus 1 into the last expression yields n is equal to 2 times k minus the quantity 2l plus 1. Be careful with our parentheses there. Now from here, that implies that n would be equal to 2k minus 2l minus 1, which I could in turn say is the same as 2k minus 2l. Remember, our trick was to convert -1 into -2 plus 1. So minus 2 plus 1, which is equal to 2 times k minus l minus 1 plus 1, which makes it clear that n is odd, which is what we wanted to prove. So notice that we started off with m plus n is even and m is odd, and we arrived at the conclusion n is odd per the statement of the original problem. That n is odd was the desired conclusion there in the original statement. So we know we're done with the proof at this point. Put our happy little square. All right, so there's the direct proof written up a bit nicer. Now let's do the proof by let me do the contradiction proof. Well, I'll go and do the contraposition. The contraposition proof was a bit more convoluted because of the logic involved, but we'll go ahead and do it. So go back to our scratch work here. What were we supposing if we're doing it by contraposition? We got to suppose n is even, and then we're going to argue that m plus n is odd or m is even. Okay. So let's start off by getting that statement down, that suppose n is even. Let's go ahead and get the definition of n being even out of the way. So then there exists a k in the integers such that n is equal to twice k. All right, so now we want to prove m plus n is odd or m is even. To prove m plus n is odd or n is even, no, it's supposed to be m is even, we observe that it suffices. We were going to prove that m being odd implies m plus n is odd. And maybe parenthetically here I'll mention what the rationale is for that. Say by the tautology, P or Q is equivalent to not P implies Q. This was our P or Q. And so instead of proving P or Q, we're proving not P implies Q. To that end, If we're trying to prove an implication, we suppose the hypothesis is true. So we're going to suppose m is odd. Then we know that there exists some L in the integers such that m is equal to 2 times L plus 1. And now we want to make a conclusion about m plus n. And we know something about both m and n separately. We know that n is equal to 2k, and we know that m is equal to 2l plus 1. So we're going to add those together to get m plus n. Now since m is equal to 2l plus 1 and n is equal to 2k, we have m plus n equals 2l plus 1 plus 2k, which is the same as 2 times k plus l plus 1, which is clearly odd. And then that's it. That's the proof by contraposition with a little bit of convoluted logic, but it checks out. And then here finally is the proof by contradiction. So for that one, we go back to the scratch work here. We're going to suppose m plus n is even, m is odd, and n is even, and then get a contradiction out of that, which ended up being an odd equals an even. So let's suppose m plus n is even, m is odd, and n is even. Then we can say there exist some integers k and l such that, I guess we need 3 integers, k, l, and j, such that m plus n is 2k, m is equal to 2l plus 1, and n is equal to twice j. Now m plus n equals 2k. That since we have individual expressions for m and n separately, we can substitute them and get 2l plus 1 for the m, substituting, and 2j for the n, and that still equals 2k, which implies that 2 times l plus j plus 1 equals 2k, but this implies an even equals an odd, a contradiction. And then that ends the proof there. All right, so there you go. 3 different proofs of the same fact, all using different logic. And, I think in this particular case, the direct proof was sort of the most transparent and easiest proof to do. The contraposition was the trickiest because we had to use some subtle logic about the or statement in the middle of the proof. Although, once you've seen that trick, it becomes sort of a standard trick. Anytime you're trying to prove an or statement is true, you can use this trick of negating one of the pieces of the or statement and showing that that implies that the other part of the or statement is true. So it seems kind of weird the first time you see it, but trust me, it's sort of old hat after you've done it a time or two and you don't think anything of it. But it made this proof seem a little bit more complicated, which it did. So I'd say contraposition is probably not the easiest proof to do. And then the contradiction was also pretty straightforward. So next, let's go on and talk about proofs of biconditional statements. We want to prove biconditional statements. Remember, biconditional statements are these statements of the form P if and only if Q. So the first method, and this is the method I tend to go to, it's sort of my default method, is to make use of a tautology. The tautology is the biconditional statement P if and only if Q is logically equivalent to P implies Q and Q implies P. So if I want to prove this biconditional statement over here, I can instead prove this and statement over here. And when you want to prove an and statement is true, you have to prove that both of the individual pieces are true. So in other words, I got to prove this piece is true and I got to prove this piece is true separately. So what you can do to do a biconditional proof is to break it into 2 proofs where you prove each of the individual implications separately. That tends to be the easiest way to prove things, but there is another way that you can do it, and when the other way works, the other way is a lot shorter and easier, but the problem is that it doesn't often work. So let me show you how to take advantage of this tautology to prove a biconditional statement. So in the problem that I have here, we want to prove that for any given integer n, n is odd if and only if n squared is odd. This is your P statement. Then you've got if and only if here. So that's your biconditional. And then over here's a Q statement. So this is a statement of the form P if and only if Q. And the first part of that statement for any integer n is sort of just stating what the universe of the problem is, right? So we're working with integers. But really it's just an if and only if statement. Okay, so to do the proof using the tautology I mentioned, you break it into two pieces. And I'm going to indicate the first piece, a forward implication. So what you want to do here is prove n being odd implies n squared is odd. And then we need to do a reverse implication proof where we prove that n squared being odd implies n is odd. Now, those are two separate proofs that we're going to do. So, I can do one of these proofs using direct proof. I can do the other proof using contradiction or whatever, right? So each proof can have its own sort of sub method. But the bigger method for proving the biconditional is to prove these two separate implications per this tautology at the top here. Okay, so let's see how that goes. So for this first implication, I would suppose that n is odd, and then I'll use the definition of odd to say, well then n is equal to 2 times k plus 1 for some integer k. And now I can sort of directly just get at n squared. N squared is equal to 2k plus 1 quantity squared, and I can FOIL that out and I get 4k squared plus 4k plus 1, which in turn can be written as 2 times 2k squared plus 2k plus 1, where we'll make note that the term in the parentheses there is an integer. So 2k squared plus 2k is an integer on account of k being an integer. So we've expressed n squared here as 2 times an integer plus 1, and that's the definition of odd. So we can conclude right there, n squared is odd. Okay, and so now we got to prove the reverse implication. Now, it turns out to be difficult to prove directly that n squared being odd equals n is odd. So what I'm going to do is do it by contraposition. So I'm going to indicate at the beginning here, I'm going to do this proof by contraposition. Okay, so to do this one by contraposition, we need to reverse the hypothesis and conclusion and negate them and prove it that way. So in other words, we need to prove n even implies n squared is even in this particular case. All right, so if we're doing it by contraposition, we'll start off by supposing that n is even. Then there exists some integer k such that n is equal to 2 times k. And now that makes it easy to work with n squared. N squared is going to be 2k quantity squared equals 4k squared. And we can factor a 2 out of that and write it as 2 times 2k squared, where 2k squared is an integer. So n squared is even, because you see that we've written n squared as 2 times an integer. All right, so there you go. There's the proof by contraposition of the converse of the original statement that we were proving up here at the top. So that's an instance where it's convenient to break it into two separate pieces and prove those two separate implications. But it's not the only way to prove a biconditional statement. In some special instances, there's a second method that applies, and the logical justification for it is that we're going to make repeated use of a certain tautology. So we have a tautology that says P if and only if Q and Q if and only if R, all that is logically equivalent to P if and only if R. So if we want to prove P if and only if R, we can break that up into, we can string together a few separate if and only ifs. So if I can separately prove P if and only if Q, and then in turn Q if and only if R, just string those together like that. Maybe I string more than two together, but the idea is to make repeated use of that tautology. And we establish a chain of equivalent statements connecting A to B if we're trying to prove A if and only if B. So let's look at this example down here. So we have x is a real number, and we're going to prove that x squared minus 2x plus 1 equals 0 if and only if x equals 1. So this is a statement where if we called that P, we got if and only if, and then we got Q here. Here's how the proof that would put together a chain of equivalencies would work. So let's start off by letting x be a real number. Then x squared minus 2x plus 1 equals 0 if and only if. So it's logically equivalent to say if that's equal to 0, then by factoring the left hand side we get an equivalent statement. That would be the same as x minus 1 quantity squared is equal to 0. But that in turn is a logically equivalent statement to saying, well, x minus 1 times x minus 1 equals 0. And remember we had this 0, what was it called? The zero product property? I had it in a box over here a little while ago. Right here. We had the zero product property that said if x times y is equal to 0, then one or the other, or maybe both of the numbers has to be equal to 0. So I want to take advantage of that here, because I've got something times something equals 0. So this is equivalent to saying x minus 1 equals 0, or x minus 1 equals 0. So that's the zero product property. And that in turn is logically equivalent to just saying x minus 1 is equal to 0, because P or P is logically equivalent to just P. And then that last statement is clearly logically equivalent to just saying x equals 1. So now if you look at what we've got this is connected with a chain of if and only ifs to the x equals 1, which is what we want to prove. So thus x squared minus 2x plus 1 equals 0 if and only if x equals 1. So if you can pull it off, this is, a very concise way to prove an if and only if statement. It sometimes works when you're proving equations involving numbers or maybe involving sets a little bit later, but it's kind of rare that it works. So I would encourage you to think of the first method that I showed you where you do two separate implications as your default method. If you happen to notice while you're doing one of the implications that the steps are all reversible, then you can turn it into one of those simpler proofs. In this proof up here, that's not a reversible proof, so I'm not going to be able to turn that into an easy one, because starting with n squared is odd. You can't reverse the logic and get n is equal to 2k plus 1. You just can't, because you'd end up having to take square roots or something like that, and it just wouldn't work out. All right, so this would be a good time for you to do a skills check on proving biconditional statements. So I have an example here that I would like you to try, and the example is here. You want to show that if m and n have the same parity if and only if m plus n is even. And what the same parity means is that, so two integers have the same parity if they're both even or if they're both odd. So when you're going to prove this statement, if you say m and n have the same parity, you're assuming an or statement. Either both m and n are even or both m and n are odd. And so that means you're going to have to handle that via cases. You're going to have to consider the case that both m and n are even, and then show that m plus n has to be even, and then also the case when both m and n are separately odd, and get m plus n as even. And then going the other way, you may want to think about an indirect approach, like maybe do a contraposition or something along those lines. All right, so maybe take a swing at that, and then we'll come back and work it together after you've had a chance to work on it. So, maybe give yourself 10 or 15 minutes to work on this one, and come back, press pause, come back, and we'll work it together. All right, welcome back. So here we're going to do this one using the first method that I showed you, where we do two implications. So we indicate which implication we're doing by using these arrows like this. So here I'm going to start off by supposing m and n have the same parity. So that means that either they're both even or they're both odd. So then I'm going to consider two cases. So in the case m and n are even, we know there exists some integers k and l such that m is equal to 2k and n is equal to 2l. Then m plus n would be 2k plus 2l, which would be 2 times k plus l quantity, which is even. And then in the other case, that m and n are odd, we have there exists, I don't know, little a and little b in the integers, such that m is equal to 2a plus 1 and n equals 2b plus 1. Then it follows, you get m plus n equals 2a plus 1 plus 2b plus 1, which we can write as 2 times a plus b plus 1, which again is clearly even. In either case, m plus n is even. And then if we want to do it the other way, I think it's going to be difficult to do it directly, because if you suppose that m plus n is even, it's hard to say anything about m and n individually in a direct way. So I think maybe I'll go by contraposition when I go this way. So just a little scratch work over here. If we're trying to prove, so what we want to prove is that m plus n being even implies m and n have the same parity. So if we do the contraposition of that, that would be m and n have opposite parity implies m plus n is odd. To say m and n have opposite parity would, without any loss of generality, would be something like, well, m is odd and n is even. So to do this proof by contraposition without loss of generality, I could just start by supposing that m is odd and n is even. And so that's the way I'm going to start my proof. So without loss of generality, which we tend to abbreviate WLOG, so without loss of generality here, suppose m is odd and n is even. The reason we say without loss of generality is that if I did the, see, what I'm really supposing here is that m and n have opposite parity. So if I did the proof where m was even and n was odd, the proof is going to go exactly the same. It's going to look, I mean, the details are only going to differ by just sort of interchanging two variables. So, it's not really going to be a different proof. So we say in those sort of situations without loss of generality. Then we know that there exists some k and l in the integers, such that m is equal to 2k plus 1 and n is equal to 2 times l. And now we can see that m plus n is equal to 2k plus 1 plus 2l, which is equal to 2 times k plus l plus 1. 2 times an integer plus 1 is odd, right? So, which is odd. And then now we've proven the contraposition. And so that's the end of that proof. Maybe I could have started off the proof by saying suppose m and n have opposite parity. And then without loss of generality, suppose m is odd and n is even. All right, so that's another example of doing a biconditional proof. And like I said, doing it in this style, method 1, tends to be my default way, unless I have some really good reason to suppose that I'm going to be able to reverse the logic. But you can see in this one, the two proofs are distinct, right? I can't really reverse the logic on these things. The first half of this proof here, there were cases, and that foreshadows something we're going to be talking about in our next method, is doing proofs by cases.